Hi class, this video is for MANOVA. So recall that everything that we're doing now, it's going to be multivariate, meaning we're going to have multiple dependent variables. So before, what we did was a multivariate t-test, the multivariate version of a t-test. So MANOVA, it's an extension of Hotelling's t-squared, because we have more groups to compare, not just two. And it's also an extension of ANOVA, a multivariate analysis of variance. That's actually what it stands for, the MANOVA. So you can think about it in two ways. It's the extension of Hotelling's, and it's also the multivariate extension of ANOVA. So here I have an example. So it's a community mental health clinic data set from California. The California Quality of Life Inventory. It has 40 items, and it has two factors: objective quality of life and subjective quality of life, and they're liker items. So here, the researcher is interested in two dependent variables: the objective quality of life and subjective. And the independent variables would be gender, ethnicity, any other demographic variables that they have as their data collection. The research question is, do all of those three independent variables, ethnicity, gender, and age, have statistically significant effects on the objective and subjective quality of life? So that's the research question that they want to answer. So they can answer it two ways: the correct way and the incorrect way. So let's talk about the incorrect way. So they could do two separate ANOVAs. So they could do one ANOVA for quality of life, and then have the three independent variables that they're interested in. That's going to answer one question just for the objective. And then they could run a separate ANOVA, which is going to have subjective quality of life and then the three independent variables. So the issue here that you have is there's two. One is a type 1 error. You're going to have the type 1 error that comes with the first ANOVA, and then you're going to have a type 1 error that comes with the second ANOVA. So once you start adding that up, that's a lot of type 1 error you can have in a single study. So that's an issue. Then there's the second issue. Those two dependent variables, objective and subjective, there's a reason why the researcher is interested in that. Like, there's a relationship between them, and when you do an analysis and separate them, you might be losing a relationship that is there. And that's actually the justification for doing multivariate, because there is a relationship between them. If you calculate the correlation between them, ideally it would be high. Or theory simply tells you objective and subjective quality of life, there's a relationship there. And when you analyze them separately, you're ignoring that relationship. Definitely make a case for this approach that it is going to be easy to interpret, especially if it's not people that live knee deep in statistics, but it's definitely not the correct approach. So what you should do if you're in this situation, or what you should recommend the researcher, is to do MANOVA. You would have the two dependent variables be subjective quality of life and objective, and then your independent variables would be the same. And MANOVA is going to account for that relationship between the two variables. And because it's only one analysis, wherever you set your alpha to 0.05, you're just going to have that type 1 error be 0.55%. So that's always nice. You're minimizing the type 1 error, which we were definitely not doing when we were doing two ANOVAs. So a little bit more about MANOVA. So if you recall, the null hypothesis for ANOVA was comparing, if you had three groups, for example, you would compare mu1, mu2, mu3. Mu represents the population mean, by the way. And the alternative was that at least one of them is not equal, or not all of them are equal. It's pretty much the same for MANOVA. It's just that we represented in vectors because of how the data is set up. So in ANOVA, we had one dependent variable, and we could have one or more categorical independent variables, and it's going to be pretty much the same for MANOVA, except we have more dependent variables, but you can have one or more categorical independent variables. Definitions. IB is going to stand for independent variable. In the old days, textbook would say that the independent variable had to be dichotomous, but it really just needs to be a grouping variable. You can have more than two groups, and those groups can be whatever you're interested in, whatever categories you're interested in, gender, handedness, or any type of experimental manipulation. So you could have more than two experimental manipulations. So between subjects are what we use as independent variables, and those are just variables that create the different groups by the groups or by the levels that you're using, and it cannot be continuous, obviously. For MANOVA, it's essentially what you're doing is essentially a between subjects ANOVA, but instead of having one dependent variable, you're going to have multiple dependent variables. DB is going to stand for the dependent variable, and this one definitely needs to be continuous. If it's not continuous, then you're better off doing some type of multivariate logistic regression or doing a discriminant analysis. So your dependent variable is just something you're measuring on all of the groups that you have. For MANOVA, we're going to have 4 different statistics. Wilks Lambda is the most popular one, and I've definitely seen articles where they at least they don't put it in the article. They don't put all 4 of them in the article. They'll just report on Wilks Lambda. But in my experience, most software will output all of them. And then there's Royd's largest root, Hotelling strays, and PSYC. Hotelling is the same Hotelling that did the Hotelling t-square. You can think of them as giant means. They're definitely not means, but you can definitely think of them like that. It's rare that you are going to be in a situation where they don't reach the same conclusion. You could have, ideally, you would have all of them reach the same conclusion. You would have the majority of them at least reach the same conclusion. If they don't, it's probably a sample size issue. And you might consider any other type of analysis, maybe not going the multivariate route. So what kind of research questions can you answer with a MANOVA? Well, you're going to have 2 dependent variables. So basically what you're answering is whether dependent variable 1 and dependent variable 2 differ by whatever grouping variable that you have. The process of MANOVA looks like this. Wow, this is big for the screen. You would conduct a MANOVA, and then you would find, ideally, well, it depends, significance. If you do find significance, then you're going to have to make a choice as to what post hoc test you should do. And there are some issues with the discussions, I guess, on what's the appropriate way to do a post hoc for MANOVA. I think the most popular one is doing a follow-up ANOVA as a post hoc, and if you still find significance there, then you would go ahead and do another post hoc like Tukey or Bonferroni or whichever one that you're familiar with. This has definitely been attributed to SPSS because SPSS just prints out the ANOVAs and people just reported that for a long time. The other option that you would have would be to do a discriminant analysis. The way this class is structured, the textbook is structured, you don't learn about discriminant analysis until later. But by the end of the semester, you will definitely have both tools. So what I would recommend is that you search what's the most appropriate one for your field, and that's the post hoc that you would conduct. I kind of mentioned this already. We have 4 different test statistics: Wilks, Hotelling, Roy's largest root, and PSYC. They are sensitive to assumption violations, so it's very, very important that you check the assumptions for MANOVA. Honestly, again, like, it's going to be very rare. Like, you have to be very unlucky for them not to reach the same conclusion, so I would not worry about it. There's definitely research on it, but it's as you can see, it's pretty old. So I feel like we all moved on and accepted that they're going to reach the same conclusion. The way you calculate Wilks lambda, and that's the Greek letter for lambda, capital lambda, you would, the way it's calculated is by having the matrices of the sum square errors for the dependent variables, the sum squares of the effects, and they're matrices because you have multiple dependent variables. It's okay. Any software that you use will give you that information. I think I already mentioned this, but all those 4 test statistics will reach the same conclusion, ideally. If they do, then you can go ahead and report Wilks lambda. It's assumed they all reach that same conclusion. If they don't, you may have a sample size issue, unbalanced design. You're violating the assumption of variance covariance. And then you would probably opt for using a univariate type of analysis. What are the assumptions? So the assumptions are usually our usual multivariate assumptions. We're going to use data from Schumacher, who uses data from another textbook that's Stephen 2009. I'll post this on Canvas, and it's a very small data set. Everything that comes from Schumacher, the data sets are just squeaky clean, perfect. It has 20 observations and four variables. So it has a method, which is going to be the grouping variable, and it has 2 achievement variables. And the research question is, do the measures of achievement differ by teaching method? So go ahead and import your data. You can use the menu option if you wish, and just make sure you select heading yes, because otherwise it doesn't look good in the variables when you do that. And this is not the actual data, this is just my generic screenshot for that. We're going to use the library PSYC, which I use pretty often now. My first command is the names command, and I'm just giving names to the 4 variables that I have in there. Method, class, achievement 1, and achievement 2. And then I use summary to see what was going on there. So I added a couple of missing data just so we could remove it in practice. So I do have a missing data in all of them. Nice. I can actually use, for this kind of situation, when it's missing in all of them, you can just go and use this command, which is na.emit, and then you put your data set, data frame, and it just removes everything. If it's a situation where you really need the data and then there's only missing in certain places, so in this case it was not missing at random, it was missing completely. That's why I needed to remove it. So then if you didn't have it like that, you could definitely try and use the mice package. So I'm going to remove outliers next. I'm going to use MANOVA's distance for that. So I just put the columns that have the continuous variables in there. This is the degrees of freedom. This is the cutoff. This is essentially that number you would get from a table. This is the actual function to find MANOVA's distance. This is the key piece of code here. Summary. Here is going to compare all of the values MANOVA's distance function found and compare them to our cutoff. If it's greater than that cutoff, then it would tell us which ones are not meeting that requirement, and those would be outliers. So in this case, we don't have anything that says false. All of them are fine. We don't have outliers. I actually didn't have to do the subset, but for some reason I left it in here. That's fine, ignore it. It's just going to be the 20 observations that we have after we remove the data. So we didn't have any multivariate outliers. Independence. So I was skimming the Schumacher text, and he actually recommends calculating the correlations between the observations, and he uses a special kind of measure called the interclass correlation coefficient. My recommendation is you leave that for multivariate type of designs. It's not that hard to calculate in R, so if you ever need it, I would just go to the textbook and look at the code. For us, independence is not really something that we can assess. If we have relationships between the observations, we will know, and we definitely should account for that. So just make sure that you have independence between your participants and you made that assumption. And then for normality, we know that we're going to do Shapiro-Wilk. We are gonna, if you have a violation of normality for MANOVA, it's not a big deal. MANOVA is pretty robust to violations of normality. It's actually the variance covariance one that can really ruin everything. And normality in general is just a hard assumption to meet. And you could have a situation where some of the variables in your analysis are not normal, but again, MANOVA is pretty robust to violations of normality. So I'm going to use the MB norm test package. I have to transpose my data. Again, I'm pretty sure there's a function out there where we don't have to do this, but I keep using this one because it's what the textbook recommended. So, and then I use the Shapiro.test function and I put my transpose data in there. It gives me the W and the p-value. That's nice. It's greater than an alpha of 0.05. So I do not reject the null hypothesis, which in this case would be that the data is normally distributed. That's nice. I meet that assumption. Setting up for assumption. So this piece of code, we're just going to transform our data into a chi-square distribution so that we can later create the QQ plots and the histograms and so on. For the most part, the code stays the same. All you ever have to change here is just the data and make sure you're pointing to the continuous variables, because otherwise you wouldn't be doing histograms anyway. Here we're going to use a histogram for the standardized residuals that we get from this piece of code, and then it creates this histogram. And it doesn't look that bad, actually. In terms of normality, it looks, it doesn't look great, but it doesn't look horrible. It doesn't look skewed. So that's nice. And then here, this is how I usually report my Shapiro-Wilk findings. We assess the multivariate normality of the two dependent variables with Shapiro-Wilk, and then you report the W and the p-value. We met the assumption. That's always nice. And you can also mention that you created a histogram for the standardized residuals, and it looked normal. That's another thing. I tend to always go with the test where you can report the numbers, because for teaching purposes, but it's also pretty valid to report the histograms. Next, I'm going to check linearity. The way we're going to check linearity, we're going to make many checks. First, we're going to check for the determinant of the correlation matrix for the continuous variables, as of course, because if it's categorical, we cannot do a correlation. This is greater than 0. That looks good. Then I check for the determinant of the covariance. It is greater than 0. Honestly, I think if you meet this one, it should be fine, because the covariance is just a transformation of the correlation. Is just not bounded by -1 and +1. So I think this would be enough. But it's pretty easy to check both, so we did. I'm going to use those standardized residuals that I got from that piece of code. And then I'm going to do a QQ plot to check for linearity. And, I mean, we have a very small data set, so it's okay that we see some, like over here we see some departures, but it's not horrible. I have definitely seen worse. So I would not say we're violating linearity. We assess that by correlation, checking the determinants, and we assess it by looking at the QQ plots. Finally, we're going to check for equality of variance covariance matrices. And for that, we use a box M test. I'm going to use the package he plots. The first argument in this function of box M is usually the continuous dependent variables. So that's achievement 1 and achievement 2 in our data set. And then over here is going to be the grouping variable, which is the first column that has the method. Remember, the null hypothesis for box M test is the variance covariances are equal. The alternative hypothesis is that they're not equal. So here I do not reject the null hypothesis, and I can say that I meet the assumption of variance covariance. Equality of variance covariance, and then you report the chi-square, which is here, the degrees of freedom, which is here, and then the p-value, which is over here. Nice. So now that we did all of that, we can actually go ahead and do our MANOVA. So here I loaded a couple of packages. Mass. I'm pretty sure mass is already loaded into the base R, but go ahead and use the command anyway. Car and psych. I already called for psych, but I'm going to do it again. So the first thing I'm doing here is that I'm telling R that the column with the method 1 and 2, it's a categorical variable. That's what factor does essentially. And it's saving it in an object called group, GRP. And that's just, I call it that so we know that those are the groups. The dependent variables are the achievement 1 and achievement 2. And I am binding those two columns and I'm storing them into another variable called DVs for dependent variables. The next thing I'm going to do is I'm going to use the linear model. And the linear model is the same way we calculate the ANOVA or a regression. The structure of the code is pretty much the same. And you're going to see the structure in R pretty frequently. So here we're going to use the function LM, which stands for linear model. Then you're going to have your dependent variable. In this case, I'm going to have 2 of them because that's what I have in my data set. Then you have the little squiggly, I think it's called tilde. And then you would have the independent variable, which is the grouping variable, GRP. Then you tell it what data set you want them to find these variables. And everything that's going to get calculated is going to get stored into output. Finally, I'm going to use the function called MANOVA. Remember, R is case sensitive, so you need to have that capital M in there. And then you're going to put whatever you calculated from the linear model into MANOVA. This is just telling R all of those analysis. I just want to say the MANOVA, basically. And then we're going to look at the type 3. So type 3, normally in SPSS or even Jamovi, you wouldn't have to select this. It's just telling R that the order in which the dependent variables were entered doesn't really matter. And then I use summary to open up everything that gets stored into MANOVA _out. And I want to see the multivariate test, so I say true to that. That's what the T stands for, true. And then this is the hardest part because the output is ugly and it's very long. So you're going to get this really long output. And then I want you to notice that we have where it says intercept. We're basically going to ignore that for our reporting purposes. It doesn't mean that it doesn't mean anything. It does tell us some information. It's just not commonly reported. So we're going to jump to a group. And this is where we're going to look at our multivariate statistics, the 4 statistics that we discussed. PSYC, Wilks, Hotelling, and Roy's greatest root. So here are the actual statistic values. I'm trying to highlight it. I just remember that the PDF doesn't let me highlight everywhere I want. So this is actually the value of PSYC, Wilkes, Hotellings, and Roy. So remember I was telling you that they're all going to reach the same conclusion? But then you freak out because you look at this and like, whoa, whoa, whoa. This F is different for all of them. That's okay because they're calculated a bit different. So the F can be different for all of them, but the p-value has to be the same. They have to reach the same conclusion. So as long as all those p-values are reaching the same conclusion, they are significant, we're fine. And at least they are to the 0.05 level. So we found significance, good. That means we can go ahead and do the post hoc, which you have options. It could be ANOVA or it could be discriminant analysis. For this one, we're going to do ANOVA. We'll learn discriminant later. To find the ANOVAs, you can use the summary AOB function, and all you have to put inside of it is that linear model that was like a first step when we were calculating the MANOVA, and that's it. It's going to give you all the ANOVAs. So what that linear model does is that it runs all the possible linear models. It can do MANOVA, ANOVA, discriminant analysis, etc., etc. And they all get stored in that output variable. And the way we ask for the one that we want is by using the different functions. So first we use the MANOVA function and we look at that output. Now we want to see the ANOVA output, so we're asking for it by using the summary AOB function. Here are the two dependent variables, and then you ask me, okay, but which one is response 1 and which one is response 2? So you're going to know because of the way they were entered, achievement 1 and achievement 2, it's going to run them in that order essentially. And I'll put a little label here later, just so you can remember what they are. And they are both significant. So what the ANOVAs are telling us is that when we compare the means for the three methods in their achievement, in the type of achievement 1, they were significant. And when we compare the three methods for the dependent variable, achievement 2, they were also significant. So that's nice. Now let's talk effect sizes. So I strongly recommend that Hawk text. I have the reference at the end. And it kind of gives us the cutoffs that we're going to use for our effect sizes. For MANOVA, you can use partial eta square, or you can actually use PSYC as your effect size. Like PSYC and partial eta square, they're the same. They're going to be the same number. And I think the MANOVA chapter in the Hawk text kind of shows the equation if you want to look at that. If not, I'll continue. So here I got the partial eta square. I use that function. I put my output in there. I said true because I want it from ANOVA. And I want the partial one. I don't want just eta square. So that's what it gave me. And then I did the same, but here in test, I actually put PSYC. And you could change this to Wilkes or Hotelling or Royce if you wanted to. But notice how they're going to be the same number. Woo, cool. Next, I'm just going to do descriptives. And I'm going to do descriptives so I can, write my report. We use the summary function, and for the most part, I think that's enough. I really wish that the summary had the standard deviation as well. It would make my life easier. But for these descriptives, I'm going to show you another function, which is describe by. And I think it comes from the PSYC package. You just put, the first argument is the data that you're using, and then the second argument is the by what. So here I want my descriptives divided by method. So, and that's what it's giving me. Method 1, it gives me all of the descriptives that I wanted to. It's kind of like the split by if we were using Jamovi or SPSS. And it just gives me the descriptives for each method. Notice how there's a couple of nans. And that's because method is a categorical variable, so you cannot really do skewness and kurtosis for that. So don't forget. It's fine. Everything's fine. So my paragraph for descriptive, I just had the first teaching method had an average achievement at 24. The second had an average achievement of 63.31. And I didn't get that just from the describe. I actually look at what the averages were for, let's look at 3 so you can see it all in one screen. I look at the means for the teaching method 3, the means for the both achievements, and then I added them, divided them by 2. And remember, round is just so I can only see 2 digits. And I did that with an R. Cool. So now let's do something more complex, which is the 2x2 between subjects MANOVA. Here we have a data set where participants were measured on their femininity and masculinity, I'm assuming with a survey, and they want to know if those two variables affect a range of dependent measures. And those dependent measures are self-esteem, attitude towards women roles, and neuroticism. Fun fact, our studio now has a spell check function, which I need to use more often, but I misspell neuroticism often, and I changed it to eroticism. So if you see it somewhere, let me know, I can fix it. My independent variables are going to be the femininity scale, so it has a low versus high. The masculinity scale, a low versus high, and the dependent variables are going to be those 3 measures that I mentioned: self-esteem, attitude toward the role of women, or women's roles, and neuroticism. It's 2x2 because each one of the independent variable has 2 levels. That's why it's called 2x2, by the way. So the research question is going to be, we want to see if the different feminine, masculine groups will score differently on any combination of the dependent variables. And we want to see how they differ on those personal factors, which are the self-esteem, attitude, and neuroticism. So the file is called master CSV. Make sure you select heading yes when you upload it. Cool. Oh, we're going to do a power analysis first. You're going to open your G-Power. So here's my G-Power. I'm going to go to F-Test, and I'm going to look for MANOVA special effects and interactions. That's what we use for between subjects. I'm pretty sure here I'm going to use 0.09. Determine. Oops. So we open G-Power. We're going to go to F-Test. MANOVA, special effects, and interactions, because we're doing a 2x2 between subjects. We're gonna put, here's the actual information over here. Our effect size is gonna be 0.05, 0.09, I'm sorry. The alpha is gonna be 0.05, and then 0.80. Cool. The number of groups that we have is 4, because there's 2 in femininity, low and high, and then 2 in masculinity, low and high. So number of groups is going to be 4. Nice. Number of predictors is 2, femininity and masculinity. The response variables are 3. Attitudes towards women's role, self-esteem, I think. And I am blanking out on the third one, but we have a third one. Neuroticism. There you go. And then I click enter. And it gives me the effect size for PSYC. It actually does that transformation. That's nice. The actual power is 0.80. It says that we need a total sample size of 79. That's not a lot of people. Let's go see our write-up. So power analysis for MANOVA with 2 levels and 3 dependent variables was conducted in G-Power. Remember to cite that. And then I gave the information on the alpha, the power, and the medium effect size. And the desired sample size was 79. So the next thing I would do is use the dim function to check the size of my data set. So I have, remember, it gives me the rows and then the columns. So I have 369 participants. We still have to check for missing data and so on, and 9 variables. So we have way more than what G-Power is suggesting. And it really has to do with us selecting conveniently medium effect size. If we had selected a small effect size, it would definitely have asked for a larger sample size. Cool. Now let's check the assumptions. So the first thing I did after I checked the dimensions for my data set was use the summary function to see what in the world was inside of it. So I have the femininity, high and low, masculinity, high and low, and I should have 9 variables. Case no is just like the ID number. Esteem, that's one of my dependent variables. It looks continuous. I'm happy as a clam. Control is not a dependent variable. Attitude towards roles, that's supposed to be continuous, and neurotic. And so this data set comes like this from a textbook, but I can tell that the attitude, the esteem, and the neurotic are probably like items from a survey added together, just from the range of it. But it's important to know that we also have missing data for neurotic. We have 62 missing data. So I use this percent missing function to figure out how much percentage of missing data I had. This function always stays as it is, like it was created to find that value. And then you're going to store whatever the apply function is doing, like you give it the data set. Remember, 1 represents row, so it's checking for missing data by row. And then you're going to apply the percentage missing function. And then I just used table to look at what it found. So it's telling me that 62 participants or rows, whichever you have in your data set, have 11% missing data. That's a lot. So even if I do this other function that I tend to use, like remove everything that has, keep everything that has less than 5% missing data, everything's going to get removed. So here you would have the option of using that option. It's going to remove the 62 people, or just using the na.emit function. Other one, it's going to do the same thing. And it has to do more with the size of the missing data than anything else. So after we remove that, we end up with 307 participants. That's still not bad. So I'm going to check my outliers as usual. First, I get the degrees of freedom over here. Notice how I'm pointing to the no miss data, and then I'm only asking for the dependent variable columns. Let me show you. 1, 2, 3, 4 is esteem. 5 control, 6 is attitudes, and then the last one is neurotic. So I'm only pointing to 4, 6, and 9. I'll add the numbers later. Cool, that's what I'm doing, all of them. I ask for my cutoff, I ask for MANOVA's distance function. Then I compare all of those values that MANOVA's distance finds to my cutoff to determine if they are outliers or not. And it doesn't say false, so it's telling me to keep all of them, and I don't have to remove outliers. I went ahead and ran this other piece of code where it's doing the comparison, and it's going to store everything in no out. So if I had outliers, it would get removed here. Here I don't have them. The only reason I continue to run this code is because later on I'm going to call on this variable. And if I don't create it, then I have to change the name here and so on. So it's just easier for me to not change my code and just go with the motions here. That's why I ran it, just in case you're wondering. I'm going to check normality again, and I'm going to use a Shapiro walk for that. I am using this package again, the MB norm test, so I have to transpose my data. And I'm only focusing again on the dependent variables. I'm using my function mshapiro.test. Remember, the null hypothesis here is that the data are normally distributed, and I'm rejecting that. So I'm saying I'm not meeting the assumption of normality, basically, based on this test. So I'm going to create a histogram next, and you're going to see that, the test is right. So I kind of create a new distribution, chi-square distribution from the dependent variables data. I ran a fake regression, and from that fake regression, I create the standardized residuals and the fitted residuals. I'm only doing this so I can create a histogram from the standardized residuals. Again, if you just check a box in this PSS, it would be doing this exactly. You wouldn't even know it's doing it. Let me show you the histogram. Yeah, that does not look normal. So the good news is MANOVA is pretty robust to deviations from normality, so you can say that. You can also use the argument of the center limit theorem. I think for MANOVA is just a better argument to say that it's robust and that you have a pretty large sample size anyway. The next thing is to check linearity. So I can check linearity various ways. I can check for the determinants, which for the correlation and for the covariance matrix, they are greater than 0. I also recommend that you check the correlations between the dependent variables. There is a rule of thumb that they shouldn't be greater than 0.90. In my experience, I feel like this rule of thumb is from when computers weren't that powerful. Because I've seen MANOVAs run when they're like 0.88. The issue that you would have there when they are that correlated is that you have to justify to your reader why you consider them two separate dependent variables, because they are so correlated that they could potentially just be the same thing. So even though you can justify it numerically and the computer is going to run it, you still have to justify it theoretically to your reader at least. The next thing I did was to run ggpairs. I know that ggpair has a lot of warning when you run it in R. I muted mine because I didn't want my notes to look ugly, just in case you get the warning and you freak out. It's normal. Let's look at this. So they're actually not that highly correlated. So we need to have good theory behind this as to why we're running a MANOVA for this, why we are using them as dependent variables. To me, I think the problem with linearity here is that these are not purely continuous data. You can see the kitty cat scratch here. It only goes up to 55, 60. Same over here, 25, 30. So what I think it happens to this data is that they had a bunch of items for neurotic or esteem, and then they added them together, or they took the average of them, and it's still truncated. Like it still goes from 0 to 60 or 0 to 30 or something, and that's why it looks the way it does. There's nothing we can do to fix that. It's just how data is for the social sciences. We're just going to deal with it. We need to have good theory as to why we're doing this, regardless. I also did a QQ plot for the standardized residuals. And yeah, you can see at the ends, you can see that it's kind of falling off the wagon in terms of linearity. So that's an issue. And I don't think the only fix for this would be a non-parametric option, which is a completely different class, or a transformation, which is also a completely different lecture. So for us, we just reported we have issues with linearity. Next, I'm going to check the equality of variance covariance. I'm using the he plots package. Here, remember, I'm using no outliers. That's the last data set that I created, and I'm only looking at the 3 dependent variables. Over here, I'm pointing at the grouping variable, which is the first column, femininity. Here, I do not reject the null hypothesis for the box M test, which is equality of variance covariance. I can say that I'm meeting the assumption, in other words. Then over here, I also do not reject it. So for this one, I did the same thing. I just pointed to my dependent variables, but for the grouping variable, I use the masculinity column. And remember, so it's the masculinity column, but it has 2 levels, high and low. So now that I'm done with checking my assumptions, I'm gonna actually run my MANOVA. And it looks convoluted, but we already did this. So we create a variable for the dependent variables, and that's why we're using column bind. So it's just column 3, 4, and 9. And that's going to be our dependent variable. Our independent variables is going to be the femininity and masculinity. But because each one has 2 levels, that's why I put the asterisk in there, because I want to check for all the possible interactions in there. Then I just call for MANOVA and I put my output here. And this is the same way we ran it before. We keep the type 3, we ask for the multivariate test, and then summary is actually going to give us the output for MANOVA. The first thing you're going to see is the intercept. So when you see the intercept, you can go ahead and scroll down until you find the first variable that you're interested in. Again, I'm not saying the intercept is not important, but for reporting purposes, we usually don't report it. It does give some information, but in APA style, you don't have to report it. So here it is. Here's our MANOVA for femininity. And everything is significant, very highly significant. And all of our multivariate tests reach the same conclusion. That's what we want. Let's look at masculinity. Again, Pillai, Wilkes, Hotelling, and Roy, they all reach the same conclusions. I know that R is annoying because it has scientific notation, but this is just a very small value. 0.00000, 14 times 3. So everything is significant for masculinity. And then now let's check for the interaction. And I know it's the interaction because it says female masculinity. Oh, so the interaction is not significant. That makes our interpretation easier. It's definitely more complicated when it is. The next thing we would have to do is do a post hoc for each of the main effects for femininity and masculinity. Before I go into that, I sort of pause to highlight some things. So I want you to notice how the partial eta squared we get from heat plots is pretty much the same as what we get in Pillai's, because remember, they're the same thing. For masculinity, we get 0.20. It's not exactly 0.20 because we are using 2 different functions. It could be they just truncate decimals differently, but it's pretty close. Over here, I got 0.07, and I'm thinking it was 0.08. Yeah, they're pretty close. So they are the same thing. The differences that we're seeing in the numbers here are just because we're using different packages. The people that create these packages might do their calculations not as detailed, differently. So let's actually interpret our output. So for femininity, I would look at the output to find this. I got the, what's it called? The effect size from Pillai's. My 7.84, I got it from the very first section of the MANOVA. And the degrees of freedom are going to be 3 and 301. Pause. Where did I get that? So I'm looking where it says multivariate test, femininity. This is my F. These are my 2 degrees of freedom. And this is just a very small p-value, 0.0000, whatever. And remember, I'm going to use this as my effect size. Pause. So for masculinity, my degrees of freedom are 3 and 301. My F is 24. My p-value is this very small p-value, and my partial eta squared is 0.20. Let me pause and show you the output. Here it is this masculinity. That's the F. Those are my degrees of freedom. The p-value looks weird because it's scientific notation, but it's a very small number. And this could also be my effect size. And we can do the same for the interaction. It's not that important because it was not significant, but you would find it in the same place. Let's go to our post hoc. So we have to do post hocs for the main effects. They're it's better. There is a better way of doing the post hoc, not just by running discriminant analysis, but even doing the ANOVA. There's another function called EC ANOVA that I find the output a little bit easier to work in. But I went ahead and just used summary AOB because I didn't want to throw any more new things at you. So I just used my function summary AOB from the output that I created earlier. Let me pause again. When I initially ran my linear model with my dependent variables, my 3 dependent variables and my 2 independent variables and all their levels, I save it into output. And then I call for the MANOVA, and it just gave me the output for MANOVA. Now I'm going to call for the ANOVAs that are stored in here, and I'm going to look at those because I'm going to interpret those as if they were my post hoc. So I'm back in the post hoc section, and then I just ran summary AOB. I put my output in there. I'm going to code this also as green. Response 1 and response 2 and response 3. So they're in the order that I enter them. So this is esteem. This is attitudes, and this one is going to be neuroticism. And then we just interpret as we usually would for an ANOVA. Here, it's significant except for the interaction for the first dependent variable. For attitudes, it's significant except for the interaction. And then for neuroticism, only masculinity is significant, at least at the 0.05 level. Here's, again, I like using this function EC-ANOVA because it calculates the effect size, the partial eta square for the ANOVA. If you want to look at that code, it's in the Andy field text, or you can just Google it. I'm sure there's examples somewhere. But again, I didn't want to throw any more new code at you, so I just went ahead and calculated the partial eta square by hand for the post hoc ANOVAs. And really, it's really super easy to calculate it. You just need the sum of squares effect, and then divided by the sum of square effect plus the sum of square residuals. So just let me show you where I got these numbers in the actual ANOVA. Remember, I'm looking at esteem here. So it would be response 1. And this is going to be the sum of squares effect, and this is going to be the sum of squares residuals. And then the round function is just so it rounds it to 2. And here I have to clean that up. I did the same for attitude and neuroticism. And these are all things I'm going to put into my write-up. That's why I am showing you where I got them right now. So what would be next? Just descriptive. That's really all we have to do. Actually, you could even take it further and do Bonferroni or Tukey. But as it is, this is a very long problem. But you definitely have that option if that's of interest to you. What I'm going to do next is just create the descriptives that I'm going to use for my write-up. For that, I'm going to use, instead of using describe by, I'm going to use a function called aggregate. So aggregate, I'm telling it I want my dependent variable by femininity, by the levels that I have in femininity, which are high and low. From where? I want it from my data called no out. What do I want? I want my mean. So here it is. For femininity, which has 2 levels, high and low, I am getting the mean for esteem and the mean for low femininity for esteem. And then I do the same thing for the standard deviation. So I have both standard deviations. Again, I want the mean of attitudes for the 2 levels of femininity by femininity. From this data set, and I want the mean and the standard deviation. And I just have this very long piece of code for each one of the dependent variables. But I also have to do it for masculinity because I also am interested in that in this data set. So I do it again. And I just copy, honestly, I just copy and paste, and I just change here femininity to masculinity. It looks really long, but it's honestly just a lot of copy pasting. And all of this are going to be the means and standard deviations that I use for my write-up. So next we're going to look into the graphs, and we're going to use a package called ggplot. So I'm not going to go through every line of this code because I'm planning on doing that when we get to the dirty data section. We'll have a whole section on ggplot. So for now, you can just run it as is. This piece of code doesn't really change much. The only thing that it's doing is that it's creating the blank background for our plots. And then I create a bar graph for each one of the dependent variables. It's team. That looks nice. Then attitudes. For each one I'm asking, it has like a stats summary function where you can ask for mean or whichever statistic you're interested in. Descriptive statistic. Attitudes. That's nice. Femininity is misspelled. I'll fix that later. And then I do the same for neurotic. And there it is. That's what it looks like. Finally, I have the write-up for each one. So you can definitely look at this when you are writing your own write-up for the homework.